we have last time we have started chemical properties of aldehyde and ketones. We will continue that. So today, okay, Saad and Rishi, only 2 students are joined right now. Okay, Ashish, for Harsh, good evening all. Okay, Yash. Yes. So next is reaction of ammonia derivatives. We will continue the reactions of aldehyde and ketones. In that it is reaction with ammonia derivatives. So you know ammonia derivative means ammonia is NH3. So one hydrogen, if it is replaced by some other group, that is called ammonia derivative. So carbonyl compound react with ammonia derivative. So first we get OH and NHG, and then water is removed, and ultimately we get C double bond NG. So this is the product formed. Means we can write it like this: H2O is removed and we get C double bond NG at the end. Okay, so first is NH2OH. Is what is the name of this compound? Or NH2 NH2. Then NH2 NH like this, or NH2 NH C double bond O NH2. These are the ammonia derivatives we are going to discuss. Even NH2 NH, what are the name of these compounds? These are all ammonia derivatives. First is, yes, anybody? Very good. Ammonium hydride. This is hydroxyl amine. NH2 is known as, okay, Subhashri Pothal, good evening. So this is hydroxylamine. This is hydrazine, and this one is, say, 1, 2, 3, 4. This is 2, 4 dinitrophenyl hydrazine. It is also called 2,4-DNP. In short, it is called 2,4-DNP. This is semi-carbazide, and this one is phenyl hydrazine. So these are the ammonia derivatives. Very good. It is hydrazine, then 2,4-dinitrophenyl hydrazine, then it is semi-carbazide. Okay. So in these reactions, reaction with ammonia derivative, it is pH controlled reaction. Why is it so? I'll let you know after the reactions, okay, in the mechanism of this reaction. So first of all, let us go through its mechanism. Then we will discuss reaction of each one of them, okay. See, we have this carbonyl group, means aldehyde or ketone. Now this carbonyl compound, when react with ammonia derivative, tell me what happened initially. You know, if medium is acidic, then what happened? Tell me. I said it is a pH controlled reaction. Medium is weakly acidic. Medium should be weakly acidic. So first of all, H plus ion will attack on it. So if H plus will attack, that definitely attack on hydrogen. So it becomes like this. Okay. After this, now ammonia derivative, when attack on this carbon, it goes like this, because you know oxygen is more electronegative, so pi electron shift strongly towards oxygen and we get NHG positive and OH, right? After getting this, you know, H is removed as H positive, okay, H as a H positive. So the H plus used here is removed, means that acid is a catalyst, then it becomes N Hg and OH, and now H as a positive ion and OH as a negative ion, means water is removed and we get, so medium should be acidic, because if medium is acidic, then this carbon becomes more electrophilic, because as O gets positive charge, so pi electron shifting towards oxygen is strongly favorable, so carbon gets complete positive charge when ammonia derivative attacks on it. But keep in mind, if medium is strongly acidic, if it is weakly acidic, it will protonate carbonyl group, but if it is strongly acidic, then it even attack on ammonia derivative and we get this product. So now ammonia derivative is not able to act as nucleophile, means it loses its nucleophilic tendency. So reaction will not take place. So pH should be of the order of 3.5, means in between 3 and 4. If it is strongly acidic, then reaction will not take place at all, right? So would you get it? G is any group, like when we have, say, when we have NH2OH, then what is G? G is OH. When NH2NH2, G is NH2. Likewise, means any group means NH2 should be there. Means one nitrogen should have two hydrogens, then only reaction takes place. Okay? Done? Now, this is hydroxylamine. In acidic medium, so H2O is removed and we get C double bond O, C double bond N OH. That is called oxide. Okay? So, if we have acetaldehyde or acetone and treatment with hydroxylamine in weakly acidic medium takes place, then we get acetaldehyde oxime and acetone oxime. That is aldoxime and ketoxime. This is aldoxime, this is ketoxime. Right? So here in this case G is OH. Sir, got it? So this is the reaction with hydroxylamine. So when hydroxylamine react with carbonyl compound, we get oxime. Okay? Now reaction with hydrazine. So on reaction with hydrazine, NH2 is removed, so we get C double bond O N NH2, means we get hydrazone. This is hydrazine. So hydrazine when react with carbonyl group, carbonyl compound, we get hydrazone. Means it is like this NH2, NH2. So instead of OH, there is attachment of NH2, right? So it is acetaldehyde hydrazone. This is acetone hydrazone. That's it. Done. Now, if we have phenyl hydrazine, then reaction with phenyl hydrazine. So we get phenyl, hydrazone. Product formed is phenyl hydrazone. Phenyl hydrazine to phenyl hydrazone. So it is like this. Here G is NH(C6H5), right? So it is NH(C6H5) and NH(C6H5). Acetaldehyde oxime, acetaldehyde phenyl hydrazone, acetone phenyl hydrazone. Okay, next is 2,4-dinitro phenyl hydrazine. So in this case is like this. 2,4-DNP derivative. It is very useful test. It is used to test carbonyl compounds, because in this case we get, what will we get? Orange or yellow PPT. So 2,4-DNP derivative has orange or yellow PPT. So if we treat the carbonyl compound with 2,4-DNP and we get orange or yellow PPT, that means it is a carbonyl compound. If not, that is a non-carbonyl compound. So it is a test for carbonyl compounds. Very important test. If any compound gives 2,4-DNP derivative test or 2,4-DNP test, that means it is a carbonyl compound, either aldehyde or ketone. Yes, Atul, it is organic. Oh, what is difficult in it? Simple. Yeah. See, NH2 and G. So what is G? Leaving NH2, rest part is G. NH2OH. So what is G? OH, because NH2 is attached to O. In this case, what is G? NH2, this NH, benzene ring, NO2, NO2. The mechanism is not important for the board. What is important, I am going to tell you. First, this 2,4-DNP test. Because sometimes question is, okay, this compound undergoes 2,4-DNP test. Okay, formula is given to you. So from that 2,4-DNP, it strikes in your mind that it is aldehyde or ketone. So first is 2,4-DNP test. Sahil, got it? Okay, any compound which undergoes or which gives 2,4-DNP test is an aldehyde or ketone. Subhashri, done? Okay. This part is important, first thing. Second part that is very important is, yes, naming is simply if it is hydrazine, the derivative formed is hydrazone. If it is hydroxylamine, derivative formed is oxime. If it is phenylhydrazine, the compound formed is phenylhydrazone. If it is 2,4-dinitrophenylhydrazine, compound formed is 2,4-dinitrophenylhydrazone. Right? Then now semicarbazide. In semicarbazide, it is somewhat tricky. See, it has NH2 group on both sides, but only NH2 group which is away from CO is reacting to give semicarbazone. This is called semicarbazone. This is semicarbazide. And this is semicarbazone. Now, question is, as it has two NH2 group, why NH2, which is away from CO, is involved in the reaction? Can you guess? Anybody who can answer this question? Why NH2, which is away from CO, is involved in reaction? Yes, tell me. Anybody? Anybody who can answer it? That why NH2, which is away from CO, is involved in reaction with CO? Reaction with carbonyl group. No. Actually, it is a case of lone pair. You know, lone pair will attack one carbon. In this case, what happened? This lone pair and CO pi bond are in conjugation. So, due to this conjugation, lone pair is not available on nitrogen of NH2, which is close to CO, because that is involved in conjugation. But lone pair on NH2, which is away from CO, is not involved in conjugation. So lone pair is easily available for attack on the carbonyl carbon. Very good. As lone pair on nitrogen of NH2 next to CO is in conjugation. So lone pair is not available on nitrogen of NH2 next to CO group. So only lone pair available on nitrogen of NH2 is that which is away from CO group. That's it. That is very important question. Why NH2, which is away from CO, is involved in reaction with carbonyl group? Any doubt in this topic? This is all about, the last two are very important. Two for DNP test as well as this semi-carbazide to semi-carbazone. Because question asked is, as it has two NH2, why only one is involved in reaction? Why not both? Okay, great. Now, and what is the significance of pH? We have already covered that addition of ammonia derivative or reaction of carbonyl compounds with ammonia derivative is a pH controlled reaction. pH required is 3.5. Weakly acidic medium is required. If medium is strongly acidic, then even ammonia derivative gets protonated and it will not act as a nucleophile anymore. Right? Next is reaction with alcohol, or we can say addition of alcohols. So alcohols are added in aldehydes means or ketones means carbon compounds in the presence of dry HCl. In the presence of dry HCl. See the reaction. Let us take a case of acetaldehyde plus ethanol in the presence of dry HCl. Okay, so in the presence of dry HCl, first product formed is this OC2H5 on one side and OH on other side, and it is called hemiacetal. It is not very stable, so it further react with another molecule of ethanol in the presence of dry HCl, and we get acetal. We get acetal as the product. Okay, so aldehydes will give acetal, but with ketones acetal formation is less favorable, rather it will form like we have ketone, acetone, then dihydric alcohol like ethylene glycol react in the presence of dry HCl and we get cyclic ketone. So with ketones acetal formation is less favorable, rather cyclic ketone is the main product. When ketone is involved, then dihydric alcohol generally react. What is this? Ethylene glycol. Right? So this is cyclic ketone. Okay? And this cyclic ketone is formed either in dry HCl or para-toluene sulfonic acid. Para-toluene sulfonic acid in the presence of para-toluene sulfonic acid. Okay? Then what is para-toluene sulfonic acid? It is like this. Okay, so we write in short PTS. Okay, rather than using dry HCl, we can use PTS. Okay, so this is about addition of alcohols, and this cyclic acetal or ketal formed can be converted back into aldehydes or ketones by using aqueous HCl. See, we use dry HCl because of that. Because if it is aqueous, then reaction is reversed. Right? Keep in mind. So these cyclic acetals or ketones can be used to protect the particular aldehyde or ketone, or either to protect or to purify, because acetal and ketal, they can be formed and we can revert back them by using aqueous HCl. Okay. Now oxidations of aldehydes and ketones. Okay. Oxidation of aldehydes and ketones. Very important topic. Oxidations of aldehydes and ketones. So you know, aldehydes can be easily oxidized to acid by using, yes, tell me, reagents. Reagents used to oxidize aldehydes into carboxylic acid. Yes. First, reagents used. Very simple question. Answer it fast. No one? Simple, we can use acidified KMnO4 or acidified potassium dichromate. If they are used, then it can be converted into carboxylic acid with same number of carbon atoms. But ketones, they are difficult to oxidize, and if they are oxidized, then we get carboxylic acid with a lesser number of carbon atoms. Am I right? For example, let us convert acetone into carboxylic acid. You know, acetone, to convert acetone into carboxylic acid, we use HNO3. Okay. So, first of all, it is converted into enol. First, there is a tautomerism. Keto form is converted into enol form. Okay. And then this enol form, in the presence of nitric acid, is converted into carboxylic acid with lesser number of carbon atoms, along with very good, along with CO2 and H2. Okay, Arjit, Ghoshal tolerance reagent. CrO3, beta, it is used to convert alcohols into aldehydes. Okay. Aldehydes cannot be converted into carboxylic acid by using that. Okay, now we will talk about tolerance reagent, failing solution, and Benedict solution. Okay. Yes. So main oxidizing agents are acidified KMnO4, acidified potassium dichromate, or concentrated HNO3. So aldehydes can be easily converted into carboxylic acid, but ketones are oxidized with difficulty because there is a breaking of carbon-carbon bond. Okay, and we use concentrated HNO3 in most of the times, and that is oxidized by a enol formation. Tautomerism takes place first, right? Okay, now as aldehydes are easily oxidized, that means aldehydes are oxidizing agents or reducing agents? Yes, tell me. Aldehydes are easily oxidized, so aldehydes are oxidizing agent or reducing agents? Say. Very good. Aldehydes are easily oxidized, so they act as reducing agents and reduces compounds containing metal ions like Ag plus, copper 2 plus, etc. under basic conditions. Okay, so there are three reagents. First is Tollens reagent. Very important question. Tollens reagent, failing solution and Benedict solution. Two are in our syllabus. Tollens reagent and failing solution. Benedict solution is not in our syllabus, but there are questions related to it, and that is similar to failing. So why to leave that one? Okay, so we will discuss all the three. First is Tollens reagent. So what is Tollens reagent? It is, sometimes question is of 1 mark, that what is Tollens reagent? So Tollens reagent is an ammoniacal solution of silver nitrate. Ammoniacal solution of silver nitrate. How it is formed? First of all, silver nitrate is treated with ammonium hydroxide. Means we pour ammonium hydroxide into silver nitrate. Okay, and in first instance we get white PPT of silver hydroxide. Okay, along with ammonium nitrate, and we continue to add ammonium hydroxide till these precipitates dissolve in it. Okay, and we get ultimately this complex. Ag NH3 positive, okay, and OH negative, okay, along with 2H2. Just balance it. 2. Now it is balanced by AgNH3 twice, OH along with 2H2. So this is ammoniacal silver nitrate solution. What we do? We have silver nitrate. In silver nitrate, we start adding ammonium hydroxide. So initially, when ammonium hydroxide is added, the solution becomes white. White PPT are formed. White PPT of silver hydroxide. Okay. We should not stop here. We start adding. We continue to add ammonium hydroxide till all the precipitates redissolves. First they are formed and then redissolves, and that solution, because of this, becomes basic. Okay, so this is this complex is formed. So clear solution that becomes ammoniacal silver nitrate, okay, along with 2H2O. So this is the tolerance reagent. Now tolerance reagent when react with aldehyde, any aldehyde, aliphatic as well as aromatic. Okay. So aldehydes reduces tolerance reagent and we get acetate ion along with silver which is deposited on the inner walls of the beaker or test tube, and that leads to the formation of silver mirror, because inside the wall, glass wall, if silver is uniformly distributed or uniformly layered, then it is also known as silver mirror test. This is also called silver mirror test. Okay, along with 4NH3 and H2. Okay, so 2 and 3 CCH5CHO. Okay, it is C6H5COO negative, but because all OH negative ion are used, so C6H5 it becomes COOH, right? Means we get acetic acid or benzoic acid along with silver. So this is called silver mirror. So silver mirror test is given by aldehydes. Ketones do not react with tolerance reagent. Ketones do not reduce tolerance reagent. So we can distinguish aldehydes from ketones by using tolerance reagent. Okay. Sorry, this is because 2 AgNH3 twice, 2 AgNH3 twice positive. So how it is neutral? Is it balanced? Tell me. 2 right, this is silver mirror, this is silver mirror test. Is it okay? Four NH3 okay, 2 Ag and H2O. Yes. 4 NH3. Anything left untouched? But it is like that only. 4 Ag, no, but it is 2 Ag only. See, ammonia are 4 times. Right? Okay. So after this reaction, now second is failing solution. So first question is, what is failing solution? It is equimolar mixture of phenyling A aqueous copper sulfate and failing B, that is sodium hydroxide and Rochelle salt. RO. What is Rochelle salt? That is sodium potassium tartrate. So it is equimolar mixture of sodium hydroxide solution containing Rochelle's salt. Okay, that is failing B. And failing A is aqueous copper sulfate. So only aliphatic aldehydes, when react with copper in basic medium, we get RCO negative, 5OH negative, RCO negative along with Cu2O. Red PPT of Cu2O are formed, cuprous oxide along with H2O. 1, 2, 3, 5, 3 H2O. 5, 6. Okay, good. So this is the product formed. So say out of aqueous copper sulfate, copper 2 plus is used. So what is the use of Rochelle salt then? Yes. Failing A has copper 2 plus. Already in failing A there is copper 2 plus. Sorry. So what is the use of failing B then? Anybody who can answer? See, failing A has copper 2 plus. It can be obtained from copper 2 plus. Actually, copper 2 plus is complexed with tartrate, with Rochelle salt. Tartrate ion in basic medium, copper 2 plus is complexed with tartrate ion, so that copper 2 plus is given at the demand of the reaction, means as the reaction demand. Okay, copper 2 plus is released by the complex only when aldehydes are there. Okay, and at the same time check the precipitation of cupric hydroxide, means precipitation of copper 2 plus in the form of precipitation of copper 2 plus in the form of cupric hydroxide. Otherwise what would happen? Copper 2 plus will react with OH negative and we get cupric hydroxide as a precipitate. So this tartrate ion, means Rochelle salt, is used to form a complex with it, so that it is in the complex form, and when aldehydes are in there, in the picture, in the solution, only then it will release copper 2 plus, and that will react to give red PPT. Okay, this is the use of failing B. It form complex with copper 2 plus. Yes, any doubt in it? Any doubt? Now third is Benedict solution. Reaction is same. Reaction remains same. Only and keep in mind only aliphatic aldehydes will react. Aromatic aldehyde means benzaldehyde even do not react. Benzaldehydes means derivative of benzaldehyde do not react with failing solution. So it can be used to distinguish between aliphatic aldehydes and aromatic aldehydes. Failing solution or Benedict solution both can be used to distinguish between aliphatic aldehydes and aromatic aldehydes. Ketones again, if aromatic aldehyde will not react, then how can ketone will react? So ketones also does not react with ketone also does not react with Benedict solution or failing solution, right? And what is Benedict solution? Again, aqueous copper sulfate, and second solution is sodium carbonate along with sodium citrate, right? Sodium carbonate along with sodium citrate. So instead of tartrate ions in failing solution, copper 2 plus forms soluble complex with citrate ions in Benedict solution. Except this, all other things are same. Sodium carbonate, you know, it is also a base. Solution is basic only, right? Okay. Now we have covered up to oxidation, and in oxidation we have done first Tollens reagent. So Tollens reagent will react with all aldehydes, means all aldehydes will reduce Tollens reagent, that is aliphatic and aromatic. Ketones will not react. Okay. Failing solution, and it gives silver mirror, it gave red PPT of cuprous oxide, only aliphatic aldehydes will react. Even aromatic aldehyde and ketone will not react with it, right? Same is the case with Benedict solution. But one ketone, that is an exception. Only one type of ketone can react with all of these. That is alpha hydroxy ketone. Alpha hydroxy ketones will react with, means alpha hydroxy ketones can reduce any one of them. How? Actually, see, this is alpha hydroxy ketone. So on treatment with ammonical silver nitrate, it gives CH3. See, secondary alcohol is oxidized to ketone. Okay, so alpha hydroxy ketones only can reduce Tollens reagent, failing solution, Benedict solution. Only alpha hydroxy ketones, keep in mind, only this one, because here ketone has no role to play, only secondary alcohol gets oxidized to ketone. alpha hydroxyketone, and one more exception. First, and formic acid can be oxidized by Tollens reagent. Only formic acid can be oxidized by Tollens reagent. Okay, there are three OH negative actually. So in this way we get CO2 to Ag plus 4NH3 along with H2O. Okay, only formic acid will react with Tollens reagent. Formic acid will react with Tollens reagent only. Okay, it will not react with Fehling solution or others. Okay, only formic acid. Done. So alpha hydroxyketones react with all or can reduce Tollens reagent, Fehling solution, Benedict solution, and formic acid can reduce Tollens reagent. So these are the two exceptions. Otherwise, aldehydes reduces all these, ketones do not reduce. That's it. Okay. Now, next is that if we have ketones, unsymmetrical ketones. See, if ketone is symmetrical, then there is no problem. It can be broken from either side, any side. Okay. But if it is like this, unsymmetrical ketone, obviously if oxidation takes place with strong oxidizing agent, there is a breaking of carbon-carbon bond near to CO. So tell me, it will break from CH3 side or CH2-CH3 side? A side or B side? Tell me. Oxidation with strong oxidizing agent like concentrated HNO3 acidified KMNO4 or acidified potassium dichromate. Yes, tell me. It will break from A side or B side? Very good. Which rule is followed, beta? Tell me. Sal, which rule is followed? What is the name of that rule? Markov-Nikov rule. It is actually yes, we get CH3 COH and CH3 COH both sides because it breaks from B side. So keep in mind, in case of unsymmetrical ketones, CO group is preferably linked to smaller alkyl group. Keep in mind, CO group will go with smaller alkyl group. Okay, so obviously breaking is from this side because this side there is a CH3, on the other side there is CH3 CH2. So smaller alkyl group is CH3. So CO will go with CH3. It remains linked with CH3. So breaking is from this side. So there is acid of two carbon. So two acetic acids are formed. Okay. Smaller alkyl group. Very good, Sahil. Next is Heliform test. Now, Heliform test. This test is given by compounds having CH3 C double bond O group, or the compound which has a group which give this group on oxidation. So either compound have CH3CO group or CH3CHOH group. I think Heliform test we have done in alcohol phenol ether as well, but we will do it once again. Okay, so these two, the compounds having either of these two will undergo Heliform test. And what is this test? Actually, let us take CH3CO NER in the presence of NaOH and X2, sodium hydroxide and halogen. So we get CH(X3) haloform, and in this CH3 is converted into haloform and RCOONA. These are the products formed: sodium salt of carboxylic acid along with haloform. So what happened? NaOH first react with X2 to give NaOX, NaX and H2. NaOH react with X2 to give NaOX plus NaX and H2. That NaOX will react with it and we get the products. The main test for it is iodoform test. Iodoform test is used to identify the methyl ketones or compounds containing CH3CHOH. How? Because we get iodoform, this is yellow PPT. So if yellow coloration appears, that means it is a methyl ketone or compound containing CH3CHOH group. Okay, so compounds. Yes, Vasant, please proceed. You can watch rest of the part afterwards. Okay. Now, see the compound like CH3 C double bond OH. It will give this test. Even CH3 C double bond O CH3. So any alkane 2-one will give this test, or in a primary alcohol only ethanol will give this test, because in ethanol there is CH3CHOH group. It can be written as CH3CHOH, right? Or any alcohol having OH on the second carbon, means alkane 2-one, and is secondary alcohol having alkane at OH at position 2, or in primary alcohol only aldehyde is acetaldehyde. Sorry, this is alcohol. So only alcohol is ethanol, right? only aldehyde which can react is acetaldehyde or any alkane 2-on, right, or acetone. They will give this test. Very important, iodoform test. Okay. So it is used to distinguish between different compounds like methanol and ethanol. So tell me, how do we distinguish second, ethanol and propanol? Third, pentane 2-on and pentane 3-on. Yes, tell me. In the first, which one will give iodoform test? In second, which one will give iodoform test? Means we can distinguish these pairs by using iodoform test. Yes, tell me. In the first, which one will give iodoform test? Out of methanol and ethanol, which one will give iodoform test? Very good. Out of methanol and ethanol, ethanol will give iodoform test, right? Because ethanol has CH3 CHOH group. Very good. In the second, out of ethanol and propanol, ethanol and propanol, aldehyde. Beta, in ethanol we have C double bond O H. In propanol we have CH3 CH2 C double bond OH. So we have C double bond OCH3 in ethanol. So that means ethanol will give this test. Okay, Sahil? What about propane 2-on and pentane 2-on? Which one will give iodoform test? Very good. Pentane 2-on. Because pentane 2-on has CH3CO group. This one. But in propane 3-on, we don't have CH3 COCH3 group. Okay. Here we have COCH3 group. So on iodoform test, sometimes we can write simply NaOI. Okay. So we get iodoform. This part gives iodoform. Okay. And rest CH3, CH2, CH2, CH3, CH2, CH2, CO. It is attached to ONA. So this one. Okay. So we can use iodoform test to distinguish these pairs of compounds. Okay, good. So this is oxidation part. Now next is reduction to alcohol. aldehydes as well as ketones, both can be reduced to, reduction means addition of hydrogen. So CHOH means H on both sides, oxygen as well as carbon. So aldehyde will give primary alcohol, and ketone will give secondary alcohol on reduction. And reducing agents used are H2 in nickel or platinum or palladium. Or instead of this, we can use lithium aluminum hydride or sodium borohydride. Any reducing agent can be used. It can be catalytic reduction, it can be with complex metal hydrides. These are the complex metal hydrides, lithium aluminum hydride or sodium borohydride. So they can be used to reduce aldehyde into primary alcohol or ketones into secondary alcohol. Right? So tell me, out of lithium aluminum hydride, can you rub it? Okay. So I will keep it. Tell me, out of lithium aluminum hydride and sodium borohydride, which one is stronger reducing agent? We have discussed it earlier. This is actually partial reduction only, right? So tell me, out of these two, which one is stronger reducing agent? Very good. Lithium aluminum hydride is stronger than sodium borohydride. Why is it so? Yes, Sahil, tell me. Why? Why? Tell me. Why lithium aluminum hydride is stronger reducing agent? Yes. It is related to bond strength. These are the cases? No, that is not the case. Actually, aluminum is larger in size than boron. So AlH bond is longer than that of BH bond, means AlH bond is weaker than that of BH bond, right? AlH bond is weaker than that of BH bond. So lithium aluminum hydride can give hydride ion readily as compared to sodium borohydride. Okay, that is the reason that aluminum hydride can give hydride ion more easily, and that is the cause of its reducing nature. Okay, that's why lithium aluminum hydride is stronger reducing agent than sodium borohydride. Yes, very good. That's why where lies the difference? Actually, this lithium aluminum hydride or sodium borohydride both cannot reduce double bond. Both cannot reduce double bond, but if double bond is in conjugation with CO group, double bond C double bond C is in conjugation with carbonyl group, then if we treat it with sodium borohydride, double bond will not be reduced, only CHO group is reduced. But if we use lithium aluminum hydride, then is it visible? Sorry, is it visible? Yes. So even double bond is reduced by, you can write CH2OH. So lithium aluminum hydride can reduce double bond in conjugation with CO group. Saturated double bond means if double bond is not in conjugation, it cannot be reduced. Okay. If C double bond C is in conjugation with C double bond O, okay, then sodium borohydride cannot reduce it, but lithium aluminum hydride, being stronger reducing agent, can reduce even double bond, right? Okay. Sad, wait for only few minutes. Okay, only two reactions we have to complete, then reduction is complete. This is called partial reduction, but there are reactions in which aldehydes and ketones are directly converted into hydrocarbons. That is called complete reduction, and there are two reactions such, that is with conventional reduction, Wolff-Kishner reduction, or red phosphorus in Hi at 420 Kelvin. These are the three reactions actually. Okay, so first we will do conventional reduction. So in conventional reduction, what we do, see, we have aldehyde or ketone with concentrated HCl and zinc amalgam. In zinc amalgam in concentrated HCl. Okay, so we get hydrocarbon. Directly they are converted into hydrocarbon. So what is the reaction actually? You can write it like zinc amalgam in concentrated HCl. Zinc amalgam in concentrated HCl. First of all, zinc react with HCl. In zinc amalgam, zinc react with HCl to give ZnCl2 and nascent hydrogens. Okay, so see, this product is formed along with H2O. So 4 hydrogens. Means this O is replaced by 2 hydrogens. Okay, So this complete reduction takes place, and say we use HCl. So acid sensitive group, compounds containing acid sensitive group cannot be reduced by this, because otherwise that group is also converted into some other group. Okay, so we use aldehydes or ketones to convert them directly into hydrocarbons by using zinc amalgam in concentrated HCl. Okay, that is called Clemenson's reduction. Second is Dharamveer Kumar. Okay, second is Wolff-Kishner reduction. Wolff-Kishner reduction. So in Wolff-Kishner reduction, the reaction is, first of all, carbonyl compound, any aldehyde or ketone, react with hydrazine. That reaction you know, we have done it. We get hydrazone, and then in the presence of base, we get hydrocarbon along with nitrogen gas. So in this case we use base. In this case we use base, and in the other case we use acid. So and if group is compound containing acid sensitive group, we use Wolff-Kishner reduction. If compound has base sensitive group, we use Clemenson reduction. Okay, and third category is carbonyl compound along with Hi in red phosphorus at 420 Kelvin. Again we get hydrocarbon. In this case, red phosphorus first react with Hi to give phosphorus triiodide. Okay, and then on reduction we get hydrocarbon. Okay, so these are the last reactions. Okay, am I right? Along with H2O and I2. So these are the products formed. Okay, so if you write H2 and I2 as well, then you have to write it like 4Hi okay, and red phosphorus and 2I2. Okay, because then it is balanced. If you write Hi and red phosphorus on the top of this arrow, then there is no need to write the side products. In organic, most of the time we skip the side products if it is not important. Okay, so these are the reduction reactions. We have completed oxidation reactions of aldehyde ketones. We have completed reduction reactions, partial reduction with lithium aluminum hydride, sodium borohydride, or catalytic reduction, and complete reduction with Wolff-Kishner reduction, Clemenson reduction, or Hi in red phosphorus at 420 Kelvin. Now, aldol condensation and Cannizzaro reaction. I have shared videos that you have to watch. Okay, and I will complete the chapter by tomorrow. Aldehyde and ketones only. Then we will start carboxylic acid. That is a part of the same chapter, but it is in the separate subunit. Right? So that's all for the day. Thank you so much. Very good, Ashish. All of you should watch those videos of aldol condensation and Cannizzaro reaction. I have explained with the mechanism, all the things required, okay, and how to predict the products. All that is included in the video. Okay, so that's all for the day. Okay. Chalo, bye beta. I will purchase that smart board as early as possible. Don't worry. Okay, then bye bye.